Um, so, again, welcome to the 5th CUAHSI Biennial Colloquium. The theme of this meeting is Finding Your Place in Big Data, Using Observations to Understand Hydrologic Processes for Predicting a Changing World. We chose this theme because we see great opportunity to really transform our science with data that's increasingly available to the hydrology community from satellites, drones, and other remote sensing instruments, from wireless in-situ sensor development, environmental observatories, and through initiatives like the CUAHSI Water Data Center and EarthCube. The spatial and temporal resolution of environmental observations is rapidly increasing, as is our computational ability to analyze it and to model it. This data availability enables really large-scale modeling capabilities like our National Weather Service, National Water Model, and other global modeling efforts. So we are gaining not only new global scale understanding, but also fundamental process understanding at local scales. And we are having new ways of looking at complex feedbacks between the scales and processes. So these advances are becoming even more critical, I think, as we face challenges of growing populations in the future, providing sustainable water resources, and predicting effects of changes in climate across the global hydrosphere. We are really lucky to have an impressive group of speakers, thanks to the efforts of our session chairs. They've already found their place in big data, but some of you, maybe like me, don't have a lot of experience using big data in your research. I've learned quite a bit helping to organize this meeting, and I'm really excited about the opportunities that this new big data frontier brings to us. So I'm looking forward to finding my place in big data this week through interactions with all of you. Okay, so without further ado, I'd like to get things started. I'm pleased to have the honor of introducing to you our Eagleson lecturer, Dara Entekhabi. This lecture is named after Peter S. Eagleson, a scientist who integrated ecology and hydrology and redefined hydrology from being an ad hoc engineering specialty to a multidisciplinary global environmental geoscience in which the green living features of ecosystems have an important part to play. He developed new models of dynamic hydrology, looking at the hydrologic cycle as the key process that links the physics, the biology, and the chemistry of the Earth system. Dara Entekhabi is the Bacardi and Stockholm Water Foundation's professor in the Department of Civil and Environmental Engineering and the Department of Earth, Atmospheric, and Planetary Sciences at MIT. He holds a BA and 2 MA degrees from the School of Geography at Clark University in Massachusetts and a PhD from MIT. He has a long list of awards, including a National Science Foundation Presidential Young Investigator Award, the American Geophysical Union's McElwain Young Scientist Medal, and also AGU's Hydrologic Sciences Award. He is a fellow of 3 societies, the AGU, the American Meteorological Society, and the Institute of Electrical and Electronics Engineers, which is, in my view, a testament to his true success as an interdisciplinary scientist and engineer. Dara's research interests target understanding coupled hydrologic processes by taking advantage of Earth remote sensing observations and development, application of data assimilation techniques, and sensor network model integration. His contributions include an understanding of land-atmosphere interactions and boundary layer processes, atmospheric dynamics and predictability, surface water-groundwater interactions, and hill slope hydrology. He is currently a science team leader of the NASA Soil Moisture Active and Passive Satellite Mission and is a science team member of the NASA Airborne Microwave Observatory of Subcanopy and Subsurface and the China Academy of Science Water Cycle Observation Mission. So Dara, we are delighted to have you here, and we really look forward to your lecture. It's Land, Water, and Energy Cycles, Coupling, Diagnosed from Remotely Sensed Global Observations.
Thank you. Thanks, Dara. Thanks. So this is what everyone had in mind for their Sunday evening. Thanks a lot for coming, and mostly thank you for the invitation to speak at CUAHSI. I really appreciate it. So what I'm going to talk about is the coupling between the three major cycles of the Earth system: the water, energy, and I dropped it there, the carbon cycle. These are the cycles that define the metabolism of the Earth system and the climate that we live in, and any perturbations we make to any one of them is going to have ramifications in the others. So the theme of CUAHSI, as Ali mentioned, is observations and data. And for that, I'm going to briefly look at the sort of the history of observations and the transformations in observations that we use in hydrology in one generation. So within this generation, we began with basically these two measurements as the sort of the workhorse of our hydrologic analysis and hydrologic modeling. There was precipitation gauges. That was the principal way of measuring it. It was using basically a coffee can or glorified versions of it. And then stream stage measurements translated into outputs from river basins. There was input and output, and hydrology was basically the discipline for transformation, therefore rainfall runoff transformation of these inputs to these outputs. That was our sort of framework and our window into the water cycle. But within this one generation, we have now added to these observations from a different platform, from a different vantage point. They are spaceborne or airborne, and therefore they are remotely sensing the surface. They're not in situ. And also, they don't measure hydrologic variables per se. They measure radiation in different channels, everything ranging from ultraviolet to low-frequency microwave. Now, how that relates to the elements of the hydrologic cycle is sort of the challenge. But they're global, and they allow mapping. So it's a totally different animal than what we had access to only a generation ago. There have been transformative changes in the technologies used as we go from one to another. But the question, and the question for this talk, is are these transformative developments parallel in our understanding of hydrologic processes and in hydrologic science in general? And to sort of make an analogy, I'm going to go to our disciplines, but first a detour into psychoanalysis. There was this guy named Jacques Lacan, famous French psychoanalyst, and he came up with this, the sort of the definition of an early stage of childhood development, which is called the mirror stage. And apparently when children are born and up to a certain age, they don't see themselves as a whole. They see themselves as arms, legs, limbs, and they just don't see that all of this is connected. And there's this thing called the mirror stage, defined by Lacan, which says that when a child, upon viewing itself in a mirror, and it doesn't have to be literally a mirror, it could be an experience, it could be a reflection in anything, but at some point, suddenly the child recognizes itself as a whole and replaces the perceptions of fragments of a body. And the analogy for that in sister disciplines is, first of all, let's look at atmospheric sciences, and then ocean sciences, and then hydrology. Again, one generation ago, this was our perception of the circulation of the atmosphere and atmospheric dynamics, a sister discipline. It consisted of basically observations of fragments of the entire atmospheric system, namely the surface winds, and hence even the names stuck. We have the trade winds at the surface, so easterlies and westerlies at the surface, and based upon that, inferring what must be a vertical component, Hadley cells, Ferrel cells, and Poirot cells. This picture of a static, but and also mostly surface-based view was really prevalent when people like classmates Dave Tarbotten and Dave General and myself were in school. This was the picture was the first picture we had in a standard meteorology course. It was a general circulation of the atmosphere, which was steady and principally zonal. And again, based upon surface measurements of surface winds. But with the advent of the vantage point of spaceborne observations, this is the picture that is really bread and butter of meteorology today. It's a turbulent atmosphere, and most of the transport of momentum, of tracers, of vapor, of heat, is done by turbulent eddies, and not this steady circulation as we have seen. So again, this is a mirror stage. This represented a mirror stage for atmospheric sciences, where they recognize the atmosphere not as fragments or extensions of the surface, but really a very dynamic fluid and turbulence as a sort of key feature of the atmosphere. This is the water vapor channel from stitching together a bunch of geostationary satellites. So it's a tracer of higher atmospheric motion. In the ocean sciences, again, when we were in school, this was the picture. The conveyor belt, a steady, slow, globally connected circulation, thermohaline circulation, where water sank in the northern oceans, and then it went around the world in various oceans. And this was the sort of perception of how the oceans work. But with satellite altimetry, again, a different vantage point, things got much more interesting. This is satellite altimetry measurement of ocean height variation. What replaced this steady global conveyor belt was a whole bunch of train of eddies that is full of turbulence, and the ocean life and biogeochemistry is really made possible by eddy mixing in these features. And also, these low frequency features like the Kelvin waves and the Rossby waves in the central Pacific became the framework for low frequency air-sea interaction, coupling the atmosphere and the ocean. Which again, these observations in the middle of the ocean can't really be done with ships and a few buoys here and there. It took the vantage point of space in order to recognize this. So ocean sciences, atmospheric sciences, our sister disciplines have gone through their mirror stage. And the next question is, what does this, is the same opportunity, the same mirror stage now open to the hydrologic sciences? And do we just sit there and it's going to come to us, or do we have to do something to change our perception or change our paradigms to move away from rainfall runoff transformation view of surface hydrology, open it up to the atmospheric branch of the hydrologic sciences, and really see it differently as just input-output analysis. So what I'm going to talk about are these paradigms. Paradigms could be thought of as models. Models encapsulate how we think the world works in a bunch of code. And again, let's take stock. We have done some of that already. And for instance, digital elevation data. These are, again, a generation ago, we had quad charts. You wanted a library and you have quad charts that you could look up and just visually look at the topography of the area which we were studying. But in 2000, there was a Space Shuttle radar topography mission, which created a fairly high resolution and at the time, fairly accurate mapping, digital mapping of the globe. So now we have a digital data set, which is the sort of the go-to or the first point of entry in any hydrologic analysis, is to look at the digital topography, delineate the drainage and the contributing area and everything else, which was really cumbersome if you were going to do it based upon this kind of data set. So that was 2000. That was 16 years ago. Now we have other missions which do the same thing much better with better technology. For instance, TandemX, the German mission, is an example. And there are other altimetry missions out there. Precipitation, again, we had rain gauges. We had, some may argue, a lot of rain gauges. But mostly concentrated in the developing or in the developed world, and certainly not including the ocean. So precipitation was just seen exactly as it was measured, drops hitting the ground. But actually precipitation, if looked at from the vantage point of space, it has a structure and has a sort of a interconnectedness to the energy cycle around the world and the water cycle around the world, which cannot be inferred from these measurements. An example of the oceans is the intertropical convergence zone and the southern Pacific convergence zone. These two features can hardly be inferred from just these measurements, and were very poorly understood. So this is an early view of precipitation from an early mission. Now we have flying around the NASA global, I never know, is that precipitation mission or precipitation measurements, one of the two. So again, new technology flying as we speak. And then the terrestrial biosphere. The terrestrial biosphere, when I was, as Holly mentioned, at the degree in geography, our biggest concern was how to come up with a color scheme so that you would not have red next to red and green next to green. This was a static classification of land coverage early on based upon ground surveys, later on based upon optical data. But now, so that was sort of how we incorporated ecology into our understanding of model building. But now we have things such as OCO2, which is a NASA mission flying right now, FLEX, a European mission to be soon flying, which what it measures is fluorescence of photosynthetic active radiation. So plants, as they receive photosynthetic active radiation, partition some of it into the photosynthetic process, release some of it as heat, and fluoresce the rest. And that fluorescence can be measured in very narrow spectral channels, and it's a direct measurement of photosynthesis, which is remarkable. It's not a correlative variable, it's a direct measurement of photosynthesis. So this is the annual cycle, for instance, zonally across. So these are sort of taking stock of what we have achieved so far with that spaceborne vantage point. Going back to the same question, beyond these, is there more opportunities open to the hydrologic sciences other than digital elevation data, precipitation, and vegetation mapping using vegetation indices, optical vegetation indices? And do we have to reimagine our paradigms and how we build models? And for that, I go back to another analogy, is that in our history, we have introduced a lot of models. Hydrologists are pretty prolific in developing models. But like any species, like any living higher order organism, or even lower order organism, models that survive are the result of a natural selection process. Okay, and that natural selection sort of makes some models go away that maybe had actually good traits, and makes some survive which may have good traits or just the right traits in order to survive that as natural selection pressure. So the pressures, those models that survive are models that can extract as much information as possible from available observations. So for instance, precipitation input and stream output. And can do so with fewest parameters, because that leads to problems with uniqueness. And also that they fit the metrics of performance. So that's a very narrow sort of channel that models have to go through in order to survive natural selection in this process. And again, it may lead to some good traits being passed on and good models surviving, and sometimes not necessarily. So for example, the conceptual hydrologic model, which should be really capital C, required that precipitation inputs and hydrograph are tracked well with a few number of parameters. And the analogy is to Darwin's finches. That Darwin, one of the insights that he provided in his trips to the Pacific was that different islands had different finches that had beak shapes that were unique to that particular island, and he related them to the feed, to the food that the birds were seeking, whether it was seeds or nuts or fruit, and as a result they developed different beaks. And again, if this is your food, precipitation and the hydrograph, then you develop a certain type of beak. But that beak may not be suitable if they change the food base for you. So now going, okay, the next step, what are the, what at least I personally see as the grand challenges for Earth system science and specifically for hydrologic sciences in this new data era. And this is really, if you pick any NRC study, these things come up one way or another because they're rather obvious grand challenges. One is to see the Earth system as humans as the principal agents of change, meaning that the rate of change that we're bringing to the world is unprecedented and on par with the variations in orbit, sun, and other big stuff that has gone on in our geologic history. Again, the rate of change, not the total change. And also that there are some things that just cannot be captured. Their physics is just too complicated in simple models. Examples are nucleation, phase change, surface physics, chemistry, and other unresolvable problems. It's just too difficult to encapsulate them into a finite number of variables that are connected to a model. And these are hardly arguably the principal sources of uncertainty and divergence among Earth system models. It's, solving the primitive equations for motion of the atmosphere is pretty straightforward. You can't get it wrong. But how you deal with nucleation and phase change in clouds, surface physics and second order aerosols, chemistry and other unresolvables is what creates diversity, problematic diversity among models. So how about specifically hydrologic sciences? What could be our grand challenges for us today and in the coming decades? And I'm going to propose two grand challenges. One of them is evaporation and one of them recharge. I should first off say that at least I'm not aware of any source of data that is a direct measurement of evaporation and recharge that can be adequately mapped to understand what's going on. There may be a flux station here, there may be some measurements of recharge there, but there's nowhere near the capability to be able to map these two fluxes in the hydrologic cycle. And it turns out, at least in my perspective, they're the two most important fluxes of the hydrologic cycle. First of all, and I give 5 reasons, these two fluxes are fluxes that are to the first order determinants of biogeochemical cycles. The biogeochemical cycles are embedded in the water cycle. Water is the ultimate scrubbing element out there. So the atmosphere with its photochemical reactor and the chemical reactor in the subsurface and all the biogeochemicals that are sort of entrained in there are due to these two fluxes. There are fluxes that link the slow and fast components of the water cycle, and that can be seen in a cartoon here. The residence time of groundwater being on the order of years, and the residence time of the atmosphere being on the order of days, and evaporation and recharge connect these through a surface component. The third one, to me, is the most interesting, is that these two fluxes are to the first order determined by vegetation, what type of vegetation and what the vegetation is doing. and that determines how much recharge occurs and how much evaporation occurs. But to the first order, they determine where the vegetation is. So they're very tightly coupled and first order determinants of one another. Recharge is a unique variable in that its scientific meaning and its practical meaning are identical. Recharge is the limiting rate of sustainable use of groundwater. So that's sort of the very obvious connection to relevance to what we do with our fresh water. And the last one is that evaporation and recharge are fluxes that we have most dramatically changed already in response to human activity, global change. Through land use change, we have changed these two fluxes not by 2%, 5%, 10%. In some places, we may have up to several times doubled or tripled them or reduced them. So these are things that we already have seen. This is part of the hydrologic cycle that has already changed by a huge amount, let alone what's going to happen with increased radiative forcing and global change due to the composition of the atmosphere. Land use change have changed these a lot. And what do we know about changes that have occurred? I wager that if we ask everyone in this room, or AGU or AMS, what's going to happen if you take a landscape and remove shrubs and put in grass, or vice versa, or some land use change? What is the sign, negative or positive, of change in evaporation and runoff? And I bet we're going to get conflicting answers. So this is to the first order. We don't even know the sign of the change that we cause. So this is a bit self-serving for those who know me. Both of them, evaporation and recharge, is very much dependent on the soil moisture profile near the surface, and we'll get that in a second. So just one slide on each of those. Recharge, I would say, is completely unobserved and unknown. Some of it may be because it's just such a difficult thing to measure, but it is important. Carbon flux by recharge is on par with ocean sink, and obviously it's a key to sustainable use of resources. This is the potential recharge of the Ogallala, and this is time to depletion. So it's a direct societal relevance as a hydrologic variable. Evaporation, we measure them at FluxNet sites around the world. Very expensive, very finicky equipment, but very accurate. But nowhere near enough to map this large component of the hydrologic cycle. Again, I would say that even the climatology is unknown. And even at these stations, this is raw data from some FluxNet sites. You see you get large negative excursions and positive excursions that reach almost to the solar constant. So obviously, it's a very noisy measurement, even where it's measured. The way we estimate evaporation right now is either as a residual or simulation output of a model with micrometeorological forcing, or with some crude closures out there. So these two fluxes, again, both due to their importance and also what we know of them right now, I propose that they're really grand challenges for the hydrologic sciences. So now going back to this focus on one of them, evaporation, the water, energy, and carbon cycle, the three major cycles that define the metabolism of the Earth system, are really linked to this flux. So how we characterize and model evaporation is going to determine how these three fundamental primary, the top three cycles of the Earth system are coupled together. And the flux is important, but we need to also know the controls of the flux. And the sort of conceptual framework is that there are like three gears that are coupled together. And if one of them slows down, because of that coupling through this flux, the other one must react. And models, Earth system models, really are trying to capture this, this coupling between the three. So these are cycles that turn together, and there's the sort of the size of the teeth and how the size of the wheels and how they are coupled together is through functions which are can be thought of as the closure function for the Earth system model. One example of the closure function over land that we care about is how evaporation is related to the over land, the principal constraint in terms of state variables, which is near surface soil moisture. This is data from John Albertson. It's a field experiment that happened some time ago in California, and this is evaporation normalized by potential evaporation, so it's between 0 and 1. And here is surface soil moisture as measured in the field. And it does what we know to be the case, is that when soil moisture goes down, there's less evaporation. When soil moisture is high, there's more evaporation. But as a closure function, does the shape of this matter? Does the slope matter? Where the inflection point is, does it matter? How does the definition and the coding of this one function in an Earth system model couple all these three together? And for that, let's start with the toy model. Just three equations, one for water, one for energy, and one for carbon. Very basic toy model. Change in soil moisture is a balance between precipitation and evaporation, which depends on surface soil moisture and temperature. Precipitation is exogenous forcing. The heat balance equation is incoming radiation minus outgoing radiation, which depends on the state variable, which is temperature, minus the latent heat of vaporization, so the thermodynamic specific latent heat times the evaporation rate, joules per kilogram times kilogram per meter squared per second, minus conduction of heat, just heat conduction. And then there's a biology component which says if you evaporate more, you fix more carbon, photosynthesis, and plants die with some time constant. So obviously these three equations, just from looking at them, are coupled together through these two state variables through evaporation. So there's some energy input, which is reduced by the state variable, which is the closure function, the evaporation efficiency, which is all important. So let's run the toy model for a closure function that looks like this. This is beta versus S. Random precipitation, the soil moisture goes up and down. You got these dry downs and then these shocks when the precipitation events happen. The surface temperature goes up and down with some random fluctuations due to, let's say, cloudiness and such. But during the dry downs, you see as the soil gets drier and drier, during the long ones, the temperature rises because you're shutting down evaporation. And then in the simple toy model, the biosphere also is happy when the soil moisture is rising, and then after a while it starts wilting and losing biomass. So three state variables. We can do a phase plot, which is kind of difficult in 3D, so I do it in 2D and then take the color scale as the third state variable. So this is B, the biomass, S, the soil moisture, and T, the temperature. And for this function, you get a phase space, which is sort of got some behavior, which hopefully your model will try to capture. Every time it rains, you jump, your soil moisture goes up. So this is the beginning of the end of the rainstorm, beginning of the dry down. So the temperatures are very low because there's evaporation. Plants are happy, the biomass is high. And then as you dry down, so this is one dry down event, the temperatures go up, become more red. And then after a while, where the biomass is increasing, it goes back down again. The plants are stressed. So this is a phase space in response to this function. You change the shape of this function, you're going to change the phase space. You're going to change how these three cycles in the state variables are coupled together. Here's the other extreme. There's no connection between them. And as a result, there's no connection between the three variables. It's just a random ball in the three-dimensional phase space. Now, the world is something in between these two. And if this thing goes like this or sharper or any other shape, is going to determine how you model these three fundamental metabolism cycles of the Earth system. So we are somewhere in between these two, as the simple toy model suggests, and it's important to get this thing right if you want to get the three major cycles right. So how do we model that the closure function in our Earth system models today? So this is going to look at the US. The workhorse of numerical weather prediction is the NOAA model, familiar to many here. And the workhorse of the climate modeling community is the NCAR community land model. And there are various variations of these all over. But this key closure function that is perhaps a few lines of code in the hundreds of thousands of lines of code that compromises the numerical weather prediction or the NCAR community model are like this. The beta in NOAA is relative soil saturation to the power F, and there's one F for the globe. And then the CLM has some functional form. So it's, important as this closure is over land, they're really treated very poorly. And people are aware of this. And there's a lot of work going on in trying to improve those. So going back to this closure function, again, Cahill, Tony Cahill. This function that was measured at a flux site was produced based upon independent measurements of evaporation using a flux tower and using independent measurements of soil moisture. This is very nice for this one site, but we want this globally. We want to know how this changes with vegetation and biomes. How does it change with soil texture? How does it change with seasons? Because there's probably a climate dimension to this as well. So in order to do that, we need independent measurements of soil moisture and independent measurements of evaporation. You can't get this out of, let's say, a data assimilation system because you're going to get back the function that you have in the model. So these two measurements have to be independent. And that has really been what I've been really trying to work towards for the last few years. So how to get evaporation and how to get soil moisture independently using direct observation. So again, back to a toy model. How do we estimate evaporation and estimate it globally, not just at flux net sites? Well, let's look at, again, a toy model, a conceptual model. We know a few things with some pretty good certainty. There's going to be a heat transport equation and a heat conservation and a gradient-driven heat flux into the ground, and that the surface boundary condition is the residual of all the radiative fluxes, which depend on surface temperature in the only one term, which is the outgoing thermal. There's the heat conduction, which depends on surface temperature, and the latent heat flux, which we had seen before. So there's state dependence at the boundary condition. So it's a very nonlinear system. The exact form of the dependence is to the fourth power for radiation, a linear for the heat fluxes, and through the integrated Clausius-Kaplan equation for the specific humidity. So let's do a perturbation analysis, linearize this whole thing in terms of perturbation. And these are some non-dimensional variables that fall out as a result. So non-dimensional time, and these are all non-dimensional, dissipating a heat. It turns out that the system is strictly dissipative, These are all positive, and this is negative, which is a good thing, so we don't have runaway temperatures. And the terms having to do with radiation, conduction, and sensible heat flux and ground heat flux come out separately for each term. The non-dimensionalization is such that sensible heat flux is 1. So we can look at the efficiency of dissipating heat, pulses of heat, by each of these components relative to 1. The radiative resistance is sort of heritage from T to the 4th business up here, so it's this quantity. Sensible heat flux, latent heat flux, is the beta, the closure function, times, actually it turns out, the Clausius-Clapeyron relationship, non-dimensional Clausius-Clapeyron. And then the ground heat flux has a thermal inertia component and the frequency of the day, as one would expect. So now we can look at the relative efficiency of dissipating a pulse of heat. And when you plot them, it looks something like this. So this is the relative efficiency relative to sensible heat flux, which is 1. Radiation is very poor. It's a very poor way of getting rid of heat. If you only rely on radiation, the perturbation is going to be there for a while. Ground heat flux is a little better, not much. But through the Clausius-Clapeyron relationship, evaporation is actually the most efficient in getting rid of heat by a factor of several, depending on temperature, because Clausius-Clapeyron is nonlinear in temperature. So it's a very good way of getting rid of heat. And remarkably, as you change your beta, you reduce that efficiency. So maybe if you can pulse the surface with heat and look on how it dissipates, and we know the rate of dissipation in all of these, we can figure out where this green curve must be in this range. And here's the same thing with some FluxNet sites. Turns out that it's actually reasonably reproduced. Now, where do we get that pulse of heat? We're very fortunate is that we have a on-off switch every day, very predictable, that comes on hundreds of watts of pulse of radiation a day, and then it goes back down. And it repeats and it repeats in a very predictable fashion. So we have a natural instrument. The sun pulses and creates a temperature anomaly, and you wait for see how that temperature dissipates. It's similar to an analytic chemistry instrument. You take a sample, you bombard it with energy, and look at the spectra of the return energy. In this case, we're looking at the thermal radiation, which is the state variable of the surface. So let's go back to our sort of toy model, but now gets a little more serious in constraining it with observation. So we have the same heat diffusion equation, the same surface boundary condition, but let's define the unknowns. The sum of the latent and sensible heat flux can be written as 1 minus the evaporation fraction times sensible heat flux. So that gets rid of humidity as a measurement. And evaporative fraction is the ratio of latent heat flux to the sum of the turbulent fluxes. Or if you put in energy balance, it's the ratio of the latent heat flux, watts per meter squared, based upon net radiation minus ground heat flux, available energy. How much of the available energy is going into evaporation? This is the partitioning, which is very important. But the whole thing is scaled by this troublesome parameter, which is the turbulent transfer coefficient of heat near the surface. It's dimensionless. So the turbulent transfer coefficient scales the sum of the turbulent fluxes. How much of the available energy is going into the turbulent fluxes, or net radiation going into turbulent fluxes? So these are two very nice dimensionless parameters. One of them looks at the sum, and one of them looks at the partitioning. And since they're based upon fluxes, they're transferable across models. All models should give the same flux. So these are the two dimensionless unknowns of this system. Our observations are satellite measurements in the infrared range, which give us an estimate of surface temperature, but they're not perfect. They got some error. And the M matrix is a projection matrix from the scale of the remote sensing observations to the model scale. And it's got a whole bunch of zeros in case there's no satellite overhead for that particular hour. So we've got the observation equation, and then we have our heat energy conservation. We've got two unknown parameters, EF and CH, now a vector. And the whole thing can be put into an objective function, J. And the two unknowns are EF and CH. You want to minimize the quadratic of the observation. So we want to minimize the difference between what the model thinks and what the satellite observes as the surface temperature. So just the quadratic term. We want to update our estimates with regards to some prior of the two critical parameters. We want to respect physics, so we have energy conservation with a Lagrange variable. And then if you want, you can put in a weak constraint for the error, so you don't exactly meet the model, but approximately meet the model. And these are the results of applying it over a region, over central US some time ago, several years ago. And this is an example of the log of the turbulent transfer coefficient, log base 10. So you get over this box numbers on the order of 10 to the minus 2 to 10 to the minus 3, which is what you would expect out of a turbulent transfer coefficient, but not mapped in space. There's the east-west gradient, which corresponds to a change in vegetation in this box between east and west. Now, this is NDVI vegetation index, obviously not used anywhere in the estimation. You only use temperature. So this is just to see if the east-west gradients are the same. You got missing values where you have clouds, and you can't sense the surface. And then let's look at the evaporative fraction, which is variable over time. This is evaporative fraction at two FluxNet sites. So this is the circles are the observed based upon turbulent eddy measurements of the turbulent heat fluxes. And the solid lines are the two versions of the model. And these are precipitation events. And you see the evaporative fraction going down during long periods of no rain and dry downs, as it should. And then it jumps when you have precipitation events and fluctuations therein. And the interesting thing is that precipitation and moisture input is not used. It's only temperature. So these up and down are inferred from temperature. And the evaporation and the circles versus lines are tracked pretty well between the two approaches. So now we have evaporation mapped from thermal remote sensing for the y-axis of this closure function. And for the x-axis at the time, 2012, all we had was really answer E to work with. For those of you familiar with this microwave instrument, it's a higher frequency, not ideal frequency, but it can give you measurements of soil moisture. And we applied it over a region in West Africa where there's a large gradient north-south in conditions, so it's ideally suited for as a test region. And we also applied it to the southern Great Plains site, and these are the closure functions that we get for these two sites, as an example. And one next thing we did was sort of sort this out. What is it? Soil type? Is it vegetation? What makes the shape of this closure function? Here's another example for more deep-rooted versus shallower rooted plants. But let's move on. That was 2012. What can we do in 2015, 2016, this past year? Same objective, same closure function, but let's use better data. And for that, for evaporation, I transitioned to something which is a really neat technique developed by Guido Salvucci and Pierre Gentin at Boston University and Columbia University, respectively. Two really neat papers that use micrometeorological station measurements. So routine air temperature, air humidity, wind speed, and soil temperature measurements. And through some hypothesis on an emergent behavior in relative humidity profile adjustment due to thermodynamics of boundary layer surface coupling. They can actually estimate evaporation from these measurements, and therefore, because they're based upon just routine micrometeorological measurements, there's a lot of good stations out there that allow mapping. And this particular paper compares it with heat flux sites, so it's validated to some extent in this paper. So this is now replacing the y-axis as the source of evaporation. For soil moisture is something that I've been involved in for a number of years, and which is the remote sensing of soil moisture from space. In order to get more accurate measurements, we need to go to lower and lower frequencies than what AMSRE or any other prior instrument had, which is in the sort of the 2.2 to 1.4 gigahertz, around 20 centimeter wavelength. In order to focus on the surface at that wavelength, you need a large antenna. And at typical altitudes that you can map the world, about 600 to 700 kilometers, you need a 6-meter dish or a reflective antenna. And the technological innovation was to stow this thing and deploy it in space once it's launched and in orbit. And the surface should be reflective in this frequency, so no losses. So the material science innovation in that. And this thing has to rotate. This large structure has to rotate in order to have a wide swath and have good revisit. So all of these have to be put together in a mission called Soil Moisture Active Passive. It's the first NASA mission dedicated to this particular hydrologic measurement. It's a mesh reflector, so it's lightweight and so forth. All of this is described in about 180-page handbook, which is available online. And I'll be very thankful if you send me an email so I can send you a printed copy. It can open up space in my office. You probably have seen this before. So one-page introduction to the mission. We have 5 objectives. These are actually in a 10-page document that we signed with NASA headquarters as a deliverable. The first 3 are sort of what you heard early on with the uncertainty in global water and energy cycle and carbon cycle science that I mentioned earlier as motivation. So basically, what is the evaporation rate and the carbon exchange, and how do they, by having a better closure function, we reduce the uncertainty of numerical weather prediction and climate modeling. And it turns out that soil moisture is not an exotic variable that's like deep space X-ray that you have to motivate the public of why we need to make that measurement. It's a variable that has everyday we have an everyday knowledge of it. For instance, this is a map, the flash flood guidance, which is put out daily on a county basis by the National Weather Service. Every day they update this map. And what it is the amount of void space available in the soil, so it's a complement of soil moisture, and it's a guidance. So in the weather forecast offices, the service hydrologist looks at this map, or the weather forecaster looks at NextRad, and if the amount of anticipated rain is more than what the soil can take, what deficit of soil moisture there is, they issue a warning. This is the drought map that is put out by various agencies, including NOAA, but also the Drought Mitigation Center in Nebraska. So again, this is a Palmer Index, which is a soil moisture accounting on a climate division basis. So again, the point is that there are applications out there, practical everyday uses of soil moisture that doesn't require much sort of convincing that it's a relevant societal variable. So the mission design L-band in order to see through the atmosphere, which is transparent. We want to see the surface. It goes through some canopy, not heavy canopy, and it actually penetrates the ground to some extent. And the sort of the system parameters for that. The launch was on January 31 of last year. It was spectacular. It went really well. The instruments came out of the box working really well. This is microwave radiation measured in Kelvin units, which can be in low-frequency microwave, very Jeans approximation. So it's really a measure of radiation. It's not a physical temperature. That's why it's so low. And over land, you see the variations due to both physical temperature, surface soil moisture, and vegetation. There's actually measurements with the ocean, but at 120, 130 Kelvin, so it doesn't show up on the scale. But there is global measurement. There was a radar which complements the radiometer. Radiometer is very sensitive to surface soil moisture, but it's coarse resolution. A radar illuminates the surface so you can achieve through processing, radar processing, synthetic aperture processing, higher resolution. And here's the backscatter, the sort of in dBs, how much radiation came back from what you transmitted over the globe. And here you see the oceans and the rough oceans that create backscatter. Unfortunately, one of the two instruments failed 2 months into the mission. So we have 2 months of radar data, but no more. But the radiometer continues to produce, as we speak, science data, which is we're using it to get soil moisture, not at the original resolution that we wanted, but nonetheless, very accurate measurement. So what I'm going to talk about mostly is based upon what is now one full annual cycle of soil moisture data from the SMAP radiometer. So this is a picture of soil moisture in volumetric units around the world for a particular few days. And now there's a full annual cycle of these measurements. The launch was on end of January, but it was 3 or 4 months of instrument checkout, so there was no science data. So just recently, we had 1 full year, 1 full seasonal cycle. So now we go back to the same thing. We got evaporation from the approach of Salvucci and Gentin, and we have 1 year of SMAP measurement. There's a lag between when station measurements appear in public archives. So just recently, and in fact, on Friday afternoon, we were able to put together these two together. So this is the preliminary plot of that over CONUS. Again, since this was Friday afternoon, I haven't had time to make a prettier picture or sort it by vegetation or location or season or soil texture. But at least independent measurements of evaporative fraction from station data versus soil moisture, you see the shape that you would expect. And here's just looking at the annual, so you have more dynamic range, and the shape is there. There's a lot of, obviously, variation with having to do with mixing all of CONUS together, which we're going to then disentangle in the coming weeks. Now, one final thing about soil moisture measurements from space. As I said, it's now coarse resolution, about 40 kilometers resolution, and its sensing depth is 5 centimeters, about. So the question is that indicative of anything in the sort of water cycle? Is that too shallow a depth? Is 5 centimeters just too shallow to be meaningful? And is 36 kilometers adequate? And for that, I want to make a distinction between water budget and water cycle. And again, soil moisture itself is a sort of a tiny player in the entire orchestra of the water cycle. And in fact, if you take it as percentage, this is sort of, we've seen these type of tables in several different venues. Obviously, much of the water in the water cycle is in the ocean. Much of the rest is in ice. And when it comes down to soil moisture, it's really, 1/1000th of a percent. Tiny, tiny fraction. In the grand scheme of things, maybe even negligible. But this is its role in the water budget. That's how much water there is in the top 5 centimeters. The question is its role in the water cycle. So using that 1 year of measurement, what we do is look at the change in storage from one overpass to another. So delta soil moisture. Soil moisture goes up every time it rains, and it goes down when you have dry downs. So this change in storage, if summed over the period of record, 1 year, at every location, and then normalized by the rate of the water cycle, gives you a water cycle fraction. How much of the water cycle is evident in the time fluctuations of this one measurement? And it turns out that it's a number on the order of 20%, just below 20%. So even though it's 1/1000th of 1% of the water budget, it's 20% of the water cycle from one instrument. And because the revisit time is 3 days, so you sample every 3 days the globe, the sort of right off the gate, the maximum it can achieve is 30%, 33%, right? So this is 20% of something that can only max at 33%. So the point is that even though it's a tiny fraction of the water budget, because of its location, sitting right at the surface between the forcing of the hydrologic cycle over land, atmosphere, and the subsurface, is actually detecting a large fraction of the water cycle. I'll skip these in the interest of time. Now, we have to sort of look at the water cycle from just more than soil moisture, so let's blank out land. This is an estimate by Simon Yue of ocean salinity, the freshwater and saltwater component in practical salinity units around the world. So it's how much fresh water is incident upon the surface and how much mixing is occurring in the ocean. And it's a map of salinity that this is dynamic, obviously, but this is average. And also wind speed can be inferred from it, which is interesting in itself. But now, so this is the state variable of the water cycle over the ocean, and over land we have the soil moisture. So now we can put them together over this 1 year of record. So this is PSU over the ocean, soil moisture over land, and when it's just a movie like this, one can sort of see features that one would expect. For instance, you can focus on the Indian monsoon. You can focus on the existing loops over the unusual precipitation that's going to appear in Australia. And then the oceans are very dynamic as well. And you kind of see, and then this is frozen ground. And then you see how the land and the atmospheric branches of the hydrologic cycle are linked. So for instance, you can see the plume from the Amazon River, freshwater plume coming out. You can see the monsoon picking up here, and then following that is a sort of a front, freshwater front that goes into the Bay of Bengal. So you see the two sort of cycles linked together in one data set. In my group, we've been sort of departing from the standard algorithm approach of the project. We've been trying to sort of look at plant-water relationship, plant-water relation. How does vegetation and soil moisture couple together, the vegetation water content and soil water content? And the measurements are sensitive to water in the past, being in the soil or in the vegetation. And we've come up with a approach that separates out the amount of water in the vegetation, which is the microwave optical depth, and that of soil moisture. And it's a dynamic variable. It's higher over the tropical forest, obviously, but there is a seasonal cycle to it, and there's even a weather cycle to it. So now we're putting these two together. We have how much soil water is being lost during dry downs and during seasons, and how much is the plant gaining. So we can see how the plant responds. And one thing we're seeing, I don't have a plot of it, I have it based upon a previous instrument, I don't have one based upon SMAP. We see that in a lot of ecosystems, especially dry tropical forests, there's a long period. First of all, there's dense vegetation, it's a forest, but then there's long periods of no rain, the monsoonal climate. We see that actually the vegetation water content picks up right after rainstorms end. It's the best conditions. Rainstorms have ended, clouds have gone, you've got lots of radiation, and the soil is wet. And the vegetation water content goes up, and then several weeks, months, depending on location and the biome, into the dry season, the plant collapses. And very interestingly, it picks up again before the next rains come, which is the leaf flushing event. So there's lots you can learn in plant-water relations by knowing the water content of the soil, dynamic water content of the soil, and the vegetation mapped globally. In the interest of time, I'll skip over some case studies that we were doing and come to the conclusion. We have now 1 year of pretty exceptional L-band global radiometry. It's a very clean data set. There's always fear of radio frequency interference from ground-based radars, telecommunication, and tracking radars. We actually put in hardware and software measures into the instruments for that environment, and as a result, it's really working out quite well in a very rough environment. We have limited duration of the radar, only 2 months, but it's a lot of data. It's really massive amounts of data that we're sorting through. It's not a product that's ongoing, but you got 2 months of global, very high resolution radar, which you can play around with. All of the data are available in near real time within 12 hours. Few hours are just getting the data from spacecraft to ground, so it's really the data is being turned around with minimal latency, as fast as the processing can be done. At 2 archives, NSIDC, National Snow and Ice Data Center, and Alaska Satellite Facility. At these sites, not only you have the data and browsers, really good browsers out there to see what data you want, and you can actually carve out a piece of data and put it in various formats, including GIS. And also at these 2 sites, very importantly, there's all the documentation. There's the algorithm, the documents, how the algorithms work, what the parameters are, and also assessment reports. How well do they validate at the validation site, and what are the flags? There's tons of quality flags, what each means. There's field campaigns, airborne campaigns that have 2 of them have occurred during the time when we had satellite overpasses, one in 2015, and one of them is going on in Iowa and Manitoba as we speak. This is MB, not BB. And it's really the retrievals over oceans and lands are giving us a coupled view of the entire water cycle. But I want to go back to the beginning part before the SMAP description, which was posed this question. This is from an earlier slide. Is the mirror stage that transformed the textbooks of atmospheric sciences from general circulation to a turbulent atmosphere dominated by eddy transport, and transformed the textbooks of oceanography, both of them in one generation, from the conveyor belt thermohair line to an ocean full of eddies and transport and mixing by eddies. Is the same mirror stage available to us? And what do we need to do with our paradigms to ingest that data, to have the right beaks, Darwin's finches, to have the right beaks for this new data source or food source? So in conclusion, to reimagine our paradigms, we have to look at the water cycle not just as the fate of rain after it hits the ground, but the atmosphere and the ocean and our domain of surface and subsurface. And we have to, now we have a vantage point of measurements from space and no longer the outlet where the stage measurement is located. So we may have to depart looking at watersheds as a natural control volume. There's no necessity for that anymore. We have to characterize the fluxes as they are, with humans as major elements, agents of change. So, you know, we shouldn't do things like naturalizing the flow before applying a model. That's taking the humans out. And I don't think there's much real estate left that you can do that with. And what is that a model of anyway? What planet? Also, clearly, if we want to make use of measurements of radiation in narrow spectral channels from space, we can't just do water balance, we have to do energy balance. And on top of that, our observables should not be necessarily the state of the hydrologic model or the fluxes in the hydrologic model. What is observable? Maybe the observable should be radiation in 5.6 gigahertz. Why not? That's an observation, and there's instruments that do that. And we have to relate that 5.6 gigahertz to the state of the model. So that's called direct radiance assimilation. So direct radiance observation equation. So our observation operator should be a radiation model that is feeding the instrument or linking to the instrument. And also the world is covered with plants that are very active and dynamically active in taking up water, releasing water, and linking the water, energy, and carbon cycle. And our alliance with ecologists has to be at the mechanistic level of how a plant functions and metabolizes. And with that, I'll thanks for your attention and your Sunday evening. Criticism. There's one person in the back.
Hi, Dr. Entekhabi. So my name is Ridwan. I'm a PhD student at Penn State. So the resolution of SMAP you said is 20 kilometer, the horizontal resolution. And what is the temporal resolution? Is it daily? Or?
That's dictated by the orbit, and it's one measurement every 2 to 3 days for a complete global map. And but because it's an 8-day exact revisit, so if you look at the time series at any one location, it's usually 1 day, 2 day, 3 day, 1 day, 3 day, 2 day. So it's almost on average every 2 to 3 days at any point on the globe. Better in the, but it's only one instrument.
And I have one more question. So the resolution of hydrologic models is around 1 kilometer, 1 to 3 kilometers. But the weather outputs, it's very coarse resolution. So do you think this might affect the performance of the hydrologic models, the conversion of the horizontal resolution?
Most definitely. I mean, this is a this is a view of the world from a global perspective. It's not a replacement of a rain gauge or replacement of local information, but the perspective of seeing how the big picture is linked. There's still applications that need to take place at very fine scale for local purposes. This is looking at the global water cycle. It's a different question in a sense.
Dara, that was a wonderful sort of view of not just the present, but I think some of the future. And I just want to take you up on your very last point, which had to do with the need to sort of work in a mechanistic way with ecologists. And because it seems to me that, and you sort of hint at this, that the vegetation is doing something very interesting. And I guess I would put out there, and I think you sort of implicitly put out there, that the vegetation is somehow integrating this mix of temperature and radiation and soil moisture and evaporation. I mean, that is what allows vegetation to exist. So what I'm wondering about is when you speak about that which we can observe and use as a way of in a sense, probing those things that we cannot observe, I just wonder if there isn't a lot we can learn just from looking at the patterns of the vegetation in a more systematic way even than we've done so far, just because I think it is sort of doing that integration that your measurements are hinting at. Does that make sense?
Yes, and the slides that I skipped were an attempt at that. The question is, what do we, with vegetation, if we want to look at it globally, what are the sources of data? Traditionally, we've had, and it's still the workhorse, and very useful. We have the normalized different vegetation index, or extended vegetation, EVI, extended vegetation index, which is looking at scattering in the near infrared and absorption of photosynthetic active radiation. It's a very nice data set that has been great. But it saturates once the leaf area index hits 1. You can't see beyond the top surface of the leaf, and clouds get in the way. So but we have long-term records of it. Then came the fluorescence, which is really exciting, and we're still trying to understand how to interpret it. And it's a direct measurement of gross primary productivity in a sense. But there's still pieces left on that. But that's still in the optical range. And one thing that I didn't show was that with being able to use very low frequency microwaves, we can measure the water content of plants dynamically. And these three put together now are really powerful in looking at what is global ecology. So it's a new discipline. And then this paradox of dry tropical forest. What triggers a plant to drop its leaves and create new shoots, new leaves, which have much higher water contents, which you see in the data, in the middle of the dry season? No clues from the environment. There's no clouds or change in soil moisture. Middle of the dry season is dry for weeks before and dry for weeks to come. The plant is doing something, and that is something an ecologist can tell us. What is the internal triggering mechanism? Where's the clock?
Thank you, Dr. Entekhabi, for the informative speech. So I'm a PhD candidate at the University of Texas at Austin. It's very informative and fundamental that you raised that soil moisture as a gate to regulate the evaporation, which is feedback to the atmosphere, and recharge, which is to the subsurface flow. So in the natural world, physical world, this is true and very fundamental understanding. But my question is, for now, a lot of models, they can capture the soil moisture fairly well. But do you think by getting a more constrained and better soil moisture from remote sensing can improve the evaporation and recharge rate? As we know, there are also lots of other processes. For example, we didn't know well enough the subsurface material that can help. And which one do you think would help better?
Actually, that is touching on a argument that I've had with colleagues and even former students, and had sometimes very loud shouting matches in meetings, is that they say that each model tracks soil moisture in its own way very well, inputs, outputs, and all that. But when you pull up the time series of the soil moisture for different models, they all have different scales, different amplitudes, different units, even the effective over different depths. So no two of them are the same, and that you have to do with CDF matching or some transformation to make them together. Their amplitudes are different because they're model states. And I see that as, yes, that's the state of affairs, but that is an unacceptable state of affairs. The reason why hydrologic models went into that sort of mode is that all we cared about was inputs and outputs, and the variable that linked them in any one model could be anything. It's not observed anyways, and it's not constrained by observations anyways. And that is, I think, just not an acceptable state of affairs. If you do surface energy balance, you have radiation, heat flux, ground heat flux, all of them are balanced together with temperature. And I don't think there is any, that sub-community of hydrologists have really done a sort of good job at accepting that our models should predict the fluxes and the state variable temperature. It's unacceptable to have a model that gets the fluxes right, but the temperature is 380 Kelvin. It's unacceptable to that. It should get the fluxes right, and it should get the temperature right. And in hydrology, we should hold ourselves to that standard. We should get the fluxes right, and the soil moisture should be the same in all models. Now, I don't think that's going to happen tomorrow, but I think we should put that challenge to ourselves. We're out of time, aren't we?
Not yet. Could you talk a little more about one of the bullets you had on, I think it was your last slide, about, the need, or maybe one before this, the departure from the view of the watershed as a natural control volume for analysis. I don't know if you're trying to put some people out of work here, but we don't need watershed. Well, could you talk a little more about that, number two? And I understand we're looking at new information and a new way of looking at things, but how does it fit in with that older way?
Yeah, maybe it's for dramatic purposes a little overstated. Okay. No, what it's meant to say is that obviously we picked watersheds as a control volume because then you don't have to deal with the fluxes other than the outlet, And that is not necessarily needed when you have measurements from a sort of a mapping point of view, because you don't have that requirement for zeroing out the fluxes on the side. And an example could be that maybe the right unit of aggregation is not a watershed, but based upon climate and vegetation type. Things. That's what I mean. And it's there's different ways of looking at units of analysis than necessarily the drainage basin. See what I mean? I mean, actually, in a watershed, probably the in a big watershed, the elevation gradient creates more heterogeneity for variables that you see from space. You see what I mean? Like anything dependent on temperature or precipitation. So it's just, if I have remote sensing data of temperature and precipitation, I would not necessarily put a watershed and average everything inside, but I would do it by vegetation, elevation. You see what I mean? It's, yes. If one of the variables you're using is runoff, definitely, but maybe it's not. Thank you. Thank you. Thank you. Went on.
That's okay.